Welcome to CognitionChunks. This information is for entertainment only. I am not trained in philosophy. Is this useful? Is this nonsense? Join me as I attempt to learn from GPT. Here is Pythagoras according to GPT. Episode 5. Math and Nature. How the Pythagorean theorem can be observed in natural formations. The Pythagorean theorem, which states that in a right-angled triangle, the square of the hypotenuse, the side opposite the right angle, is equal to the sum of the squares of the other two sides, a superscript 2 plus b superscript 2 equals c superscript 2, can be intriguingly observed in various natural formations. This connection not only highlights the intrinsic mathematical patterns found in nature, but also demonstrates how fundamental mathematical principles manifest in the physical world around us. Honeycombs. One of the most visually striking examples of geometric principles in nature is the honeycomb structure created by bees. While not a direct illustration of the Pythagorean theorem, the efficiency-driven hexagonal packing seen in honeycombs can be linked to geometric and mathematical principles similar to those Pythagoras explored. Bees construct hexagons, which are one of the most efficient shapes for close packing and minimizing the use of material, wax, while maximizing strength and storage space. The principles underlying the construction of these hexagons involve understanding spatial dimensions and efficiency, concepts that are foundational in geometry. Spider webs. Spider webs often feature radial and circular patterns that can align with geometric principles. While the webs themselves are not direct applications of the Pythagorean theorem, the way spiders calculate distances and angles when constructing their webs can be an indirect application of geometric principles, including triangle optimization for stability and coverage. Each thread intersection in a web forms multiple triangles, and while it's a stretch to apply the Pythagorean theorem directly, the creation of these triangular patterns demonstrates how geometry is used by spiders to create efficient and structurally sound webs. Mountain slopes and elevation changes. The elevation change along a mountain slope provides a direct application of the Pythagorean theorem. Imagine hiking from a point at the base of a mountain directly to a peak. If the distance from the base to the peak along the ground, base of the triangle, is 5 kilometers, and the elevation gain, height of the triangle, is 3 kilometers, you can calculate the slope distance, hypotenuse, using the theorem. This practical application is often used in navigation and mapping to provide more accurate distances for hikers or to help with planning construction projects in mountainous terrain. River bends. Rivers often meander and create bends that form segments of circles and ellipses, shaped by the physics of water flow and sediment deposition. While the path of a river bend isn't a direct application of the Pythagorean theorem, understanding the dynamics of these bends involves calculating distances and changes in direction, elements that can be broken down into triangular components for analysis in more complex mathematical modeling, including applications in hydraulic geometry. In river bends, particularly in meandering rivers, the geometry can be simplified into segments that approximate right triangles, which can help hydrologists understand river dynamics. Consider a river that creates an oxbow lake, which is often shaped like a crescent or a loop. The distance a river travels, the arc along the bend, and the straight line distance, chord, between 2 points on the bend can form the legs of a right triangle, with the river path making up the hypotenuse. For instance, if the chord measures 100 meters and the river path measures 120 meters, you can apply the Pythagorean theorem to determine the height of the triangle formed, giving insight into the river's slope and sediment deposition patterns. This analysis can be crucial for flood modeling and river navigation. Snowflake symmetry. Snowflakes exhibit a hexagonal symmetry that can be broken down into equilateral triangles, each of which implicitly relies on Pythagorean principles to maintain uniformity and structural integrity. Crystals. Crystalline structures are perhaps a more abstract, yet profound, demonstration of geometric principles in nature. The angles and the structured repetition in crystals can sometimes form right triangles and other geometric shapes that directly relate to mathematical rules. The arrangement of atoms within crystals frequently adheres to specific geometric patterns that minimize energy states, aligning indirectly with principles underlying the Pythagorean theorem about distances and spatial relationships. The angles and distances between points in the crystal structure can often be described in terms of right triangles, where the theorem helps explain how molecules bond and organize. Star constellation measurements. Astronomers use principles related to the Pythagorean theorem to measure the distances between stars in a constellation. By viewing stars as points in a three-dimensional space, they can calculate the distance between any two stars if the distances to Earth and the angle between the line of sight to each star are known. This application is critical in the field of astrometry, where precise measurements between celestial bodies are necessary. While the Pythagorean theorem itself might not be directly observable in the more complex and often chaotic forms of nature, the underlying principle of finding relationships between different parts of a whole is deeply embedded in natural phenomena. Observing these patterns encourages a deeper appreciation for the mathematical order underlying natural structures and promotes a broader understanding of how fundamental mathematical principles like those discovered by Pythagoras are integral to the structure of the natural world. Thank you for joining us for another Cognition Chunks. Please like and subscribe.